Hello, I hope you can hear me. I hope you can hear me. Hello, hello, hello. All right. So we've done a lot of things in Power Systems Analysis. And it's just and so let's start. So we're looking at the last thing, and then we're going to prepare for our paper. This video should last for about 45 minutes, so I'll be quick. All right. You're looking at how to solve loaded systems, how to find the fault current, or let me say fault analysis on loaded systems. Instead, we said that we can do this using either the direct method or the Thevenin or superposition method. Thevenin or superposition method. All right. So let's start. So I'm just going straight into the slides. Okay. All right, so as usual, first thing you must know how to draw. Okay, so let me take the question you to explain. So we have this diagram. So we can see that this is a loaded system. Yeah, we can see this is a supply, a generator, through a transformer, through a line, through second transformer, then to the motor. So it's loaded. So let's try to show this. So now we are thinking about direct method. So we're looking at direct method. Alright. So first thing is to draw. Okay, so if you check, first you have a generator. We said generators are represented by what? By an EMF source behind their subtraction reactance. So this is, let's say, generator. This is the subtraction reactance of the generator, so EDG prime prime. Then we see that it will have to go through a first transformer. Please be looking at the question. A second transformer, a first transformer, the line. First transformer, the line, then a second transformer here, then to the motor. So the motor is represented by subtraction reactance, and then EMF source. So this is motor, this is SDM prime prime, and then all of them are referred to a common reference. Yes. So this is the drawing. So this is the drawing. I hope it makes sense, right? It makes sense. Yeah. So now let's go back to the question and read. Let's see what the question wants us to do. So the question says that we have a synchronous generator, and a synchronous motor, each rated 25 megavolt amps, 11 kilovolts, having 15% subtransient reactance. So the rating of all of them are 25 megavolt amps, 11 kilovolts, and the X is 15%. So let me say 0.15 X. This is a what? This is a S. This is a V. Alright. So the transformers are also rated 25 megavolt amps, 1166 with leakage reactance of 10%. So transformer, when the transformer is 10%, the X is 10%. The reasons why everything is there. I'm going to be quick, so just refer to the question for the parameters. Okay. Now you can see that they all have a base MVA of 25, right? Yes. So that was the motor is drawing 15 megawatts. The motor is drawing 15 megawatts at 0.8 power factor leading, and the terminal voltage of this. So let's come. So when a symmetrical fault occurs at the motor terminal, so a symmetrical fault occurs here. So we have the fault occurring here. This is a motor, right? Yes. So the fault is occurring here. Capital F is where the fault is. So that just before the fault occurred, the voltage of the motor was what? 10.6 kilovolts, and the power was 15 megawatts. Now, if you are doing direct method, first thing you have to find the pre-fault conditions. You have to find the pre-fault conditions. Pre-fault conditions are what? Are pre-fault current. Pre-fault current. Or let me say here, IM, like for motor. So pre-fault motor current, the not is for before. And then pre-fault voltage. So you always use, in direct method, you always use the pre-fault conditions or pre-fault parameters to find the fault, or after the fault, the post-fault parameters. Alright. So let's see. So first, how to find this our VM naught. Okay. So how do we find our VM naught? We're given that when the fault occurs, it's operating at 10.6 kilovolts, right? But the actual rating of the motor is 11 kilovolts. It was in the question. So in per unit, the voltage, the pre-fault voltage will be this 10.6 kilovolts over 11 kilovolts. That gives 0.9636 per unit. So what are we doing? We are finding pre-fault conditions, like before the fault occurred. What is the per unit voltage and per unit current there? Then now that the fault has occurred and they are all feeding into the fault, what will the current be? Sure, so let's see. So now let's find the post-fault. So now we have to find I naught, right? We know I is what? We know that P is equal to I Vn cos phi. So I is equal to P over Vn cos phi, right? This Vn here is the this Vn here is this one, initial Vm. So I have to also find P naught. Okay, so I have to also find P naught because I know V naught, but what of P naught? P naught is also a certain power, right? Now they say that when before the fault occurs, it's operating at this, but the actual rating is 25 megavolt amps. So assuming this as unity power factor here, because they didn't give us the power factor, means it's a unity power factor, meaning that the P here is also 25 megawatts. So because they didn't give us the power factor of this motor, it means it's unity power factor, hence P is 25 megawatts. Therefore, P naught in per unit is given by 15 over 25. I'll give it 3 over 5. That's 0.6 per unit. So therefore, I naught is given by 0.6 over 0.9636 times cos phi. They give us the power factor at the when the fault occurs, 0.8. So cos phi is 0.8. So this whole thing is occurring at a power factor leading, so the angle is cos inverse of 0.8. So if you do this correctly, you get 0.7783 angle 36.9. 0.7783 angle 36.9. Now, what have we found? We are seeing that initially, initially, this is the current flowing through the motor, current delivered into the motor, and this 0.63963 is the voltage across the motor. So let's see, let's draw and let's see. So here's how the circuit looks like. The circuit looks like this. So we know that for the generator, I'm having my EJ prime, right? I'm having my X here. Then I'm having this is the terminal of the motor. So I'll see all these impedances here. So I'm having 1, 2, 3. Get here. Then the voltage at this terminal, post fault, will be here. Is the voltage at the terminal. So Vm naught. And the generator is supplying that Im naught to the motor. So right now we will use this circuit. We know Vm naught. We know Vm naught, right? Yes, we know I naught. We know all these impedances. So we can use this circuit to find Ij prime. So steps. Let's see. First step, find pre-fault conditions. Second step, find Ej. Did I say Ij? I meant Ej prime. If that's what I didn't say. So you find Ej prime and Em prime using their respective circuits. Using their respective circuits. I'm coming. Alright. So this is a circuit for the Ej prime. So I'll say therefore my Ej prime is given by MV naught plus Im naught multiplied by this total impedance. This total impedance that you see here. You get it? J. Oh yes, J. This is a reactive component, so J, like this. So that's what was done here. You get it? So we know this Vm naught here. So this operations are performed in complex numbers. Okay, so this, then we have J x total x. So this is the subtraction reactance transformer line transformer again, multiplied by I naught. I naught is here. Then also use the motor circuit. You know that for a motor, that one is rather delivered to. So I'm having the subtraction reactance. I'm having my motor here. So if this is my Em prime, know that one the current is coming to it. Your Vm is supplying to the motor. So here then this Em prime is given by this minus this voltage drop will give me here. This is supplying, then some will drop before it to get here. So this is given by Vm naught minus Ij I naught multiplying this impedance here. So that's understanding. So that's what was done here. So you find your Ej prime and your Em prime. So that's the steps I've written here. So first, find pre-fault conditions. Find Ej prime and Em prime using their respective circuit. Then third, now the fault has occurred. It's a short circuit fault. So this is a short circuit fault like this. A short circuit fault. Remember we said that when a fault occurs, the generators in the motor, what they do, they feed into the fault, right? So it means that now that this fault has occurred, what will this generator produce into this part? So now we have our Ej prime and Em prime. Now we have Ej prime and Em prime, right? All right. So now I'll say that okay, I'm having my EGN prime here, which has a certain value I know. Then I'm having my X, I'm having my transformer 1 line, transformer 2, then where the fault has occurred. So I'll use this circuit to find my IGN prime. That's the current generated or produced by the presence of the generator. So here IGN prime, I is what? Ohm's law. EGN prime over X total. Yes, so now find IGN prime and IM prime at fault. I changed the song. So same, we also find, so now for the EM prime part, I'm having something like this. I'm having EM prime, this, then the fault here. So here, so I'll say my IM prime is given by EM prime over this X here. So that's how you go about it. So that's it. So that's how you go about it. You get it. So now just take this part of the circuit here. Find your IGN prime. Take this part. Find your IM prime. And they are both feeding into the fault. So they will sum to give you the fault current in per unit. You get it. So now find IF. Now IF is equal to IGN prime plus IM prime. But this is in per unit. Now we have to find the fault current in amps, right? In amps, like actual fault current. So we have to find your I base. So same thing. I base is what? S base over V base times root 3. Root 3 times V base. Find your I base. Multiply it by IGN base to find IGN actual, and IM base to find IM actual, and then you sum them together. So that's it. So you see, so this is it. So IF is here, it's a sum in per unit. Find your base current, multiply this by base current, and then you find it. All right. Yeah. So this is how you use the direct method. This is how you use the direct method to evaluate the things. It's like, yeah, to do the loaded system in the symmetrical fault analysis. Sure. Now let's see how to use the Thevenin method. So with the Thevenin's method, okay, please follow me, okay. If you must find only fault current, like find the, you see the question we saw right now, we're supposed to find the current produced by the generator, current produced by the motor, before we should find the fault current. But assuming the question just says find only the fault current. Yeah, we don't care about the other currents in the other branches. Let's find only fault current using Thevenin. You use this circuit. Here. Use this circuit here. VM naught in series with Thevenin reactance. VM naught in series with Thevenin reactance. Then we have the impedance in the fault path like this. So fault impedance, that's it. All right. So let's see. How we can solve that question we solved. This question we solved, we got a fault current. We got a fault current to be this. Right? This is a fault current. Minus J11 239 amps. So let's see. So same. Find the pre-fault condition. So we got VM naught to be what? We got VM naught to be 0.9636. So you say you find XTH, right? So the original circuit is what? Is this. You always find XTH from your original circuit. So this is EJ prime X X X X. Then now motor impedance, motor voltage. So if the fault occurs here, find the Thevenin's resistance or Thevenin's impedance. With that Thevenin impedance, first thing, short circuit voltage source, right? So short circuit here. Then stand at the fault. So open the fault. Stand at the fault. And look through these terminals. Which if you stand here and look through this impedance, which terminals will you see? If you stand here, you see this side, right? So this part, let's say this part will give me X1 in parallel with this side. So X1 in parallel with this is my X2 in parallel with X2. So if you are current and you are coming here, what will you see? You see here and you see here. So this is the total impedance. That will give us our XTH. So you find your XTH. Now, don't forget it's a short circuit fault. A short circuit fault means that what? This ZF is what? It's like this. So this is what we are doing. So we know VM to be 0.9636. XTH, we know XTH to be, XTH is, when you solve, you get your XTH to be, let me go to the question. Hey, sorry, I missed the question. You get XTH to be, okay, they didn't solve it that way. Oh, I didn't bring my book too. Please hold on. So you get XTH to be J0.1125. So if you're supposed to find IF here, I is just equals what? V over R, right? So Ohm's law. So I is equals to 0.9636 over J 0.1125. So when you do that correctly, you get the fault current to be add the J to it. So you become what? You get minus J minus. So you get minus J 8.565. So let's see that's what we got as a fault current when we solve this one. So you can see fault current in per unit was this. So you see, so actually if you are given a loaded question, right? If it's MCQ, we'll see, you can't tell you what to use. So probably the determining method is faster. If you must find just fault current, because see what we did though. What did we do? We found pre-fault condition. We did VM naught is equal to that 10.6 operating out over 11, 0.9636, right? Then you find your XTH, short circuit EMF sources. Stand at the fault level and find your XTH. Then that's all. IF is VM naught over XTH. So if you are not, if MC, it's not even A4, because this one is MCQs, he can't restrict you. So if you have to find fault current only, just go ahead and then use this one. Okay. Now, what if you are supposed to find the branch current, like in the question, in the actual question, you're supposed to find the fault current due to generator, fault current due to motor, before they say find the actual fault current. So here, this is the equivalent circuit to use. You have your VM here. All right. So we have VM nodes here, but this time your XTH, you will not Kelvinize it. You only short circuit. Is like, how do I say it? You are finding your XTH, right? So after you short circuit the EMF sources, what do you have? You see that here we have subtraction reactance of generator, first impedance, second impedance, third impedance to the fourth level, then second the motor. So it's like you are Kelvinizing, but then it's still in the expanded form. Then you have your fault impedance, because it's short circuit. So just short circuit your impedance like this. So this is your, let's say, XDGM prime prime, XDM prime prime. This is your X of transformer 1, X of transformer 2. This is your X of line. So here to find your VM naught from pre-fault 10.6 over 11, 0.9636. So we have this. Now, how do we find the fault current? So here is the same thing. You want to find IF, right? So you do your IF, so you compute this impedance. So just like the XTH we found, same way you find your XTH. So you find your XTH to be equal to what we had, which is this X1 parallel X2. What we did, same thing. What did we get? We had J 0.1125. Then you find your IF, same. So you get minus J 8.5653. So we have our IF. Same thing. But then here we want to find so this is fault current, but we also want to find IJ prime prime and IM prime prime. So this is a current due to generator and current due to the motor. Current due to the motor. Alright. So let's see how we'll do that. This is a what? It's a parallel branch, right? So when I put all here together, I'll get X1. And here I'll get X. So here's what you do. Use current divider rule to find the current coming here. So that current is called change in IM. And then the current that will come here, call it change in IG. So we'll get current divider same. So we know IF, right? So if you want to find change in IM is just what? This impedance, I think, is J 0.45 over total impedance J 0.6 times IF minus J 8.5653. Then same, find your change in IG by doing change in IG. So we'll use this impedance. So J 0.15 over J 0.6 times minus J 8.5653. Yes, it's. I'm going fast because of time, so that you can have time to revise and watch. So pardon me, but that's what you do to find your IM, to find your change in IM and change in IG. This change in IM and change in IG we found here, they are not IG prime prime and IM prime prime. They are the change due to the fault. So here's what we'll do. Here's what we'll do. We to find your IG prime prime, it is just this change in IM plus the initial current. So here, when you're finding your VM naught, you have to also find your I naught, as we did, as the P naught over V cos phi angle cos inverse of phi. You do that thing and find your I naught. You follow? So when you find your I naught, you come and add that I naught here. So let me call it IM naught here. But watch something. Watch something, okay? Watch something. I can tell you, and then I want to show you so that in case you forget, you can see where it's coming from. So the actual circuit, what do we have? We have what? We have EJ prime prime, right? We have this XDJ prime prime. We have XT1. We have XL. We have XT2. We have XDM prime prime. We have EM prime prime. Sorry. So this is the actual circuit, right? So here I'm showing that what I'm showing that the current is moving. What the current is moving, the IG prime prime is to flow this way into the fault, right? And my IM prime prime is also flowing where? In this direction. Let's see the Thevenin equivalent we are using. We are using VM naught. This, right? And then we said that our fault current is going this way, IF. So sorry, because my fault current is going this way, the IM prime prime, the change in IG I found is going up, and the change in IM I found is also going up. So that will somehow give me the IF. But in the previous one I was drawing, I drew it down, so that was a mistake. Okay, so it's supposed to be this way. So I have IG prime, change in IG, change in IM. So now how do I find IG prime prime? IG prime prime is given by what? If you check, is equal to IG naught, right? Or let me say IM naught. IM naught to flow this way. IM naught, I'm coming. So right now I'm talking about post fault. So let me change the current I've shown. Post fault. We are adding the change in current to the post fault current. Post fault means this must not even be here. So post fault, I'm having the IM not flowing this way and entering the motor this way. So my IG prime prime is given by, if you check, the change in IG and IM naught are all flowing in the same direction. So it will be IM naught plus change in IG. So the IM naught you found using that P naught over V cos phi something something will come here. Then change in IG we found will come here. But your IM prime prime, if you check, we are showing the IG prime coming. I want to show you here. So here we are showing the IM prime to be going up, change in IM to be going up, and then this one is going. So this here is to be equal to our change in IM minus this one is coming down, so minus IM naught. Yes, so that's how come these formulas are here. So it's just because of the direction of the actual diagram compared to the Thevenin equivalent direction of the current indicated. So that's how we have it. So you check, so these are in per unit, and we check they are the same. So if you want to find the actual, find your base, multiply by this. Yeah. So that is it. So that's it. So that's it for the loaded systems using the direct and the Thevenin method. So we've seen, we went through these questions yesterday. We saw all these questions yesterday too. Yeah, so yeah, please kindly take time to read this side. While load. Sure. So please read this side, read all of this side, okay? So if I give you a question, how do you know whether it's loaded or unloaded? If it's unloaded, if it's loaded, it means there's a motor at the, or there's a load connected at the output. So a motor is a load. So generator drives a motor or other loads, right? So see this one. There's no load. It's just through generator transformer over then to the fault. There's no load connected here. But if you check, so here too, there's no load. Generator, then impedance is no load, no motor. Same for here. Generator, no load, no motor. But then here, so here to see they're all generators. But here, generator supplying through to the motor, so it's loaded. Yeah. This is something there's no. Yeah, okay, but the fault is not carrying at the terminal of the motor. Get it? So it depends on where the fault is carrying. So that's it. Sorry. Yeah, so that's how you go about it. Okay. I think we've been on for 37 minutes. Oh, that was fast. Come again. Yes, please. It's up to the algorithm for load flow study. So the mission will be up to this side. It will be up to here. Yeah. Up to this side. Yeah. So this side, if you can look through it and try to understand it, okay? I'm sure you can wrap your head around it. I want us to have time to revise the plenty videos and then our own stuff. So I want to end here. I want to end the stream here. Alright, please, all the best, okay? Have a wonderful exams.